Good afternoon. Every day, our body follows a similar cycle throughout the day. We sleep at night, and we work throughout the day, and we have lunch around noon. And later in the evening, we'll wind down and get ready for bed, and it will repeat the next day. These cycles of day, or in Latin terms, circadia, has been repeating for as far as we could remember, that most of the days we don't even think about it at all. But nevertheless, we all have to admit that these cycles, they affect our daily work and even health from a fundamental way. Therefore, for decades, scientists have been studying them in details, and because of the difficulties in studying these systems, due to the reason that the control centers in human brain, a lot of the experiments are done in the mouse, and in more technical terms, these cycles are called the circadian rhythm. Like I said earlier, we study the mouse brain in order to understand this system. And just like us humans, the mouse brain also have a small part called suprachiasmatic nucleus in the middle of their brain, and it consists about 10 to 20K cells. And if you're a biologist, this might be what you're picturing in your head, which is really sophisticated neural interactions. But physicists love to simplify things. My name is Yian, and I am from the physics department at Northwestern University. And from our study, we simplify these models into a network like this. How it works is, for each neurons, we simply consider them as a dot on these plots. And if two neurons are connected in any ways, we simply draw a line between them. And this is what I study. You might have already noticed that there are two different colors of these neurons. This is because we categorize them into two main neuron types, and they serve slightly different functions. One is called VIP, the other one is called AVP. And they each emit bioluminescent data that is shown here. And for healthy individuals, these signals should follow 24-hour per cycle periodic behavior. And my goal is to study these signals and see how differences among these dots on the plot could affect their collective behaviors. Before I talk about how diversity works for these neurons, let's first take an example of how diversity works in our society. Not long ago, just a few decades ago, our society have a lot of workplaces that consist homogeneous populations. For example, a lot of scientists were male and a lot of nurses were female. But just a few decades later, right now, we all understand, regardless what fields you're in, it's almost always better to have diverse backgrounds of people as they bring in different opinions on things where new ideas may emerge. So in a simple line, we could consider this to be diversities among individuals would lead to a better collective performance. So my study is to see if this simple principle also applies for individual neurons and their collective behavior. Now you might ask, what does diversity for neurons even mean? To study that, we first need to remove these lines between the neurons, so now we could look at them as individual isolated neurons. And they might be of different sizes, they might be of different shapes, and more importantly, they might have different cycle lengths when they're by themselves. And because if there's one most important feature that your circadian rhythm must follow is it should be in synchronization with the 24-hour day-night cycle. So we specifically pick the cycle length as the diversity parameter that we study. On the other hand of the story, we also need to quantify how to characterize their collective behavior. And just like before, we first need to add these links back. So now all these neurons are working as a whole group. Here is a typical signal that we might collect from them when they're connected together. Each of the fine lines on this plot is the signal from one individual neuron, and the thicker line in the middle is their collective behavior. So again, our healthy human or mice should have these 24-hour or 1 day per cycle periodic behavior, but this may not always be the case. Under certain circumstances, these behavior might be lost, and your circadian rhythm might show a chaotic and non-periodic behavior. And this is not what we want, so we call the top panel as good behavior and the bottom as not so good. Moreover, physicists like to use numbers to assign to different things, so we call the top panel as synchronization. And this is a quantifiable variable. A larger value corresponds to a better collective behavior, while a lower value is not as good. Okay, now we have both sides of the story figured out. Now we're ready to take a look how they come together. Let's consider a simple example where all the neurons are of exact 24-hour cycle length when they're isolated. You might think, since they're already at 24 hours, when we simply put them together, the collective behavior should also be 24 hours and it should work perfectly. But this is actually not the case. We actually see that if all the neurons are of exactly 24-hour cycle with no variance at all, the system collective behavior is most likely to be chaotic, and this is not what we want for our circadian rhythm to do. On the other hand, if the group of neurons we have is slightly different in cycle length, but still close to 24 hours, when we wire them up together, the system actually shows exactly what we want. They follow the 24-hour cycle per day, and they're working in synchronization together. Moreover, with more modeling work and data analysis, we see that there's actually these shaded area if we plot the collective behavior on the y-axis and the diversity on the x-axis, where diversity actually improves the collective behavior of the system. Now, moving back to our daily experience of the circadian rhythm, if you ever suffer from jet lag or have trouble falling asleep at night, the hope is my study will give some useful insight to this in the near future. And lastly, with a better understanding with your circadian rhythm now, I hope everyone could have a restful night of sleep tonight. Thank you.